Then we come to our next speaker, and this is Dr. Kim-Anne Lebourg. Kim-Anne is group leader, functional nutrition in Nestlé Research, and she's an R&D expert in nutrition as well, and her area of expertise is in carbohydrates. So her research is focusing on defining innovative nutritional concepts to improve the nutritional quality of products to reach a balanced diet and different health benefits. So you see now some data on how we can apply science in the real world. So Kim-Anne will share her presentation on using digital tools to optimize nutritional value of foods and meals to guide towards healthy diets.
Thank you very much, Petra. Good evening, everyone. Thank you very much for attending our symposium. My only disclosure is here. I'm employed by Nestlé Research, and thus I don't have an additional slide. So just following what was shared before by Regan, just let's go back in time and see. This is the first food composition table that was shown in 1818. It's written Table de Nutrition. It has very few ingredients, very few data. And now, if we jump back to today, what do we have? We have plethora of data. It can be at the ingredient level, the recipe, the food. We have dietary intake data from multiple countries. We can characterize the diet. We have dietary surveys. And then we have plenty of set of nutritional recommendations. So, of course, the complexity has drastically increased. And then the level of analysis that we can do, of prediction that we can do, has also massively increased, and we cannot work as in the past, very obviously. So this is really where digital tools can come into play and can provide a very useful insight. So before digging into that, I just would like to put the definition that I work with during this presentation, because nowadays we speak a lot of digital in the field of AI, and for sure AI is part of digital, but it's not all. So a digital tool refers to any software, application, or device that is designed to assist or enhance various tasks, processes, or activities in the digital realm. And these tools are typically used to create, manipulate, store, or transmit digital information. So what does that mean in the context of food and nutrition? So there are three very distinct categories where we can use digital apps, digital tools. First is to create product recipe. Second is to calculate the nutritional quality of meals and diets, and all of that in order to optimize the health, and then hopefully be able to develop algorithms that can tailor both the recipe and the diet to the health needs for personalized nutrition, for example. One thing that's very critical in all of these steps is the four following. So first, the data quality, because any app, any digital tools is, of course, as good as the data that comes in. And here, I don't want to speak about analysis, but more what comes in order to build a tool. So this is what we will focus on. I'd like you also to pay attention on the algorithm building. We are all using different apps. You may track also what are your intakes. As we are all scientists here in this room, I'd like you to reflect and think about what is the algorithm behind the app that I'm using. Can I trust it? Is it very simple? Is it very complex? So just open question to keep in mind. Is there scientific validation behind the different tools that we are using? Is it just a black box that somebody has developed and put out in the market? Or is there some science behind? Another open question that I'd like you to keep in mind. And finally, the user interface. Because of course, if there are developers, product developers, tech developers who develop these tools, it's good that somebody use them, and then they might be user-friendly, being it for product developers or for users. So I will go a bit through all of these four areas. And because this is the field I know best, I will focus on an example for prevention of type 2 diabetes. So if we think of type 2 diabetes, what do we want from a product design? We want it to be low glycemic, to have a low glycemic index. Then, at the diet level, what do we want? We want, of course, the diet to be low on glycemic load on the daily basis, weekly basis, but also the most important recommendations are that it's high in fibers, whole grains, and also possibly caloric reduction in case of overweight. And finally, on the health benefit, all of that in order to reduce postprandial glucose response and to minimize the glucose excursion. So let's go through these 3 different examples and how are digital tools being developed to help on that. So I'll first focus on product design. How can we use digital tools? So to develop a low glycemic index product, what is needed is to have the glycemic index. And this is measured through an ISO-certified method that implies a clinical trial, at least 10 volunteers. These are administered either a test product or a control, and then the blood glucose is measured over 2 hours. So the question here is, how could we use digital tools to simplify this process in order not to test multiple products before having a good product that's tasty, that's good for health, and mostly that has a low glycemic index? So here, this is the nutrition science part, and without going too much to the details, glycemic index or glycemic load is really reflected by 2 types of nutritional components. The carbohydrate component that will contribute to the glycemic index, and which is schematized here in the middle. These are all the carbohydrate sugars. We can have mono, disaccharides, starch. And then there are all the components that would contribute to decrease the glycemic index, which can be the fiber, but also fat and protein, which hinder the access of the glycemic component to the digestive enzymes. So what is very important here is to have a very detailed knowledge and composition of the sugars and the glycemic component. And here I'm not only speaking about the carbohydrate that is declared on the nutrient facts or the sugars, but how far can we go, how detailed can we go? Hannah mentioned earlier the raw versus the ripe banana. For sure it will have an impact on glycemic index. If we speak of the different fibers, yes, there are the soluble, the insoluble, but within those, there are also multiple groups, and they will affect differently the glycemic index. So without going to the details, all of these components are very critical to have a detailed knowledge, and here this is an example of several monosaccharides, disaccharides, polysaccharides that have been characterized on the glycemic index. So with all of that, we can integrate that into a mathematical formula that allows to predict the glycemic index. So that was for the algorithm building, the scientific foundation. Now, how can we validate that? So this algorithm has been built using several data and then validated against an in vivo trial, of course. So this is an example of 46 breakfast cereals that have, for which the glycemic index have been measured in silico, predicted in silico, and then measured in vivo in healthy volunteers. And we can see that there's a very good prediction with a correlation coefficient of 0.9. The correlation is very similar for the glycemic load. Now, what you may notice is that there are a couple of products with the triangle that are not very well aligned. And when looking back to this data, we notice that these are those that contain chocolate, breakfast cereals with chocolate. And what do chocolate contain? Polyphenol. So these are very specific ingredients, specific components that will further affect the glycemic index. And these are all the additional components that we can then further integrate into database characterize in order to gain in precision. So here I would like to show you an example of how this looks like. This is not extremely user-friendly, but this is extremely simple. So for a product developer, what they would need to do is to enter here the ingredient that have been characterized, the amount in a recipe. All of that are the fixed factors to characterize all the different sugars, carbohydrates, and then the serving size. And then we can see very rapidly what would be the predicted glycemic index. Here we see we have 62. It may be in the medium range, and if we want to go to a lower glycemic index, then we can play with the recipe, add, for example, whole grain barley instead of refined wheat flour, and see immediately how would the predicted glycemic index behave instead of going through multiple clinical trials. So this is how a first example of digital tools can help on product development. Now, what is, of course, interesting is to see how that complies for a diet level, because, of course, somebody will never consume only one product. It's always part of a meal, part of a diet, and a product only plays so much of a role. So how do we bring that to a higher level? So this has been covered already. We know we have dietary recommendations. We know that there are multiple nutritional factors that affect cardiovascular diseases. And here the question is, how can we translate those into a score that's easy and that can advise and help for guidelines for meals and diet? So here what we consider are 9 relevant nutrients, and I'll give you more details on how those were selected. But the idea would be ideally to be able to play with a very large database of ingredients, of recipe, food, culinary matches, in order to give recommendation and help to have a balanced meal and diet. So when we have a product, we have the nutrient facts, we can read them. It becomes more complex when we want to characterize the nutritional quality of a meal, because the meal, again, contains different ingredients, different food, different product. So what was done here is to look at was to develop a score looking at what would be the recommended amount. So to make it simple, I'm really not mastering this remote. So we have here the different components. There's a recommended amount that's found basically between the MDR, so the acceptable micronutrient distribution range. So it's for each of these nutrients, a score of 100% would be given. And then if the level would be found between these two cutoffs, then the score would be 100. If it's lower by half, it would be a score of 0, and if it's more than 50%, it's also a score of 0, and everything in between would be proportional. So then a score of 100 is attributed to all of these nutrients. When we speak of nutrients to limit or to decrease, such as sodium, added sugar, saturated fat, then there's only a 0 for the upper limit because there's no really a minimal amount. And then all of that is also integrated with the energy intake, which is the first level of personalization because it's adapted to gender, age, BMI, for example. So here, so based on that, we have a score. The maximum score is 100. That would be the optimal diet quality or meal quality. And just as a first simplification, it's very difficult to have all of these nutrients in a meal, in a recipe available from restaurants. So the first step was really to see, is there any possibility to simplify, not to have to measure all these 16 nutrients in the food, to have them characterized by the restaurant, by the food providers. And here it was, so we use a dual approach. One, an expert judgment. We know there are critical nutrients that needs to be there, added sugar, sodium, saturated fat. So those need to be there. And then it was also a data-driven approach. Which one of those nutrients would have no impact on the score if they were removed? And then we ended up with 9 nutrients, and we can see that the correlation is still very good, and that only with 9 we are already able to characterize the nutritional quality of a meal. So these are the 9 nutrients found in the end: protein, calcium, total fat, fiber, potassium, iron, sodium, saturated fat, and added sugars, and all of that proportional to the energy intake. As a validation, of course, if you have a meal score, it needs to be better and to reflect some acceptable and recognized score. And here we use the healthy eating index that was already described earlier to check whether there's a good correlation between the meal score and the healthy eating index. So this is a subset from the NHANES from 2011 to 12, and here we took women between 31 to 50 years old, and we have a sample size of 155. And what we can see here is that there's a relatively good correlation between the meal score and the healthy eating index, again showing that the meal score is able to reflect the diet quality in this population. This is also transferable to other geographies, and for example, these are data from the Philippines, and we can see here that the Philippine actual diet is relatively low, with a score of 50 on average, so we would consider that a healthy score is above 70, and this is exactly what we see from exemplary meal plans from local guidelines. What should be the recommended menu plans, and these are all above 70, 75. So this again shows that the score is able to discriminate the nutritional quality, and also that there's indeed a gap at population level, and there's really a way to improve the nutritional quality of the diet in the Philippines. So this is how it looks for users, and this is an interface that has been now rolled out in more than 70 countries. So using a database of more than 200,000 recipes that are tagged and that have been scored, the user can see, okay, what's the score of my recipe? Select a recipe, then see the score. For example, here this is 52. By clicking on it, the user would be able to see what are the different components of the score. And then what is really nice and where AI is also used is to advise on how to further improve the score. So for example, here, if the user wants to add a dessert, for example, we can see that adding a nice coffee would probably not modify the score by much. Adding a fruit salad would increase it by 12 points, and a berry cake would decrease it. So the way that AI is also involved there is that there will be, of course, user preferences. So then the tool can also advise on the most preferred recipes, the most preferred ingredient, on the personalization based on allergies, on food preferences. And also there are some culinary rules, because you don't want your tool to advise you to pair brown rice with pasta, for example. Even though it would be extremely healthy, this is not something that we would do. So this is where the product development and all the background is extremely important. So just coming back to the type 2 diabetes, if we want to advise on a specific health benefit, how can we do that? So the previous example with the meal score that I showed was really based on the global population. So to adapt that to a specific population or health benefit, we need to adapt these rules. So this is the example for diabetes, but then it can be, of course, deployed for other diseases, and it has been the case to improve gut microbiota, for Crohn's disease patients. So it can really be adapted to all the different diseases. So for type 2 diabetes, what we want is that we would like to provide ideally a 7-day of structured meal plan with 3 main meals, breakfast, lunch, and dinner. There should be options of healthy meals with a score above 70 for all of those. At least 20 grams of fibers per day. So here we move away from the product and recipe, but really go to the day level. Good distribution of macronutrients, and a limit on daily glycemic load. So coming back to this algorithm that I showed initially to calculate the glycemic index of the product, here the challenge is really how do we move from the product to the diet to the day. And it was already complicated to have all the distribution of the different sugars, carbohydrates for a product, but of course this is impossible to have this characterized for the day level. So here there was again a lot of simplification steps developed. How can we compensate for starch? So starch was estimated to be carbohydrate minus total sugar. What if we have missing sugar, we don't have total sugar declared? What about the soluble, insoluble fiber? So you can see here all the simplification steps that are needed for any digital tool development. And in the end, the 5 nutrients that were used are carbohydrate, total sugars, fibers, fat, and protein, which is much simpler than the more than 15 parameters that were used for the prediction of the glycemic index. The future enhancement are really also to use AI in order to estimate the total sugars, because we know also now that using this tool by having the nutritional composition or the list of ingredients can allow to accurately predict the added sugars, which is often not declared. So in terms of validation, what again is important is to see what do we get from such algorithm. And what you see here is the original algorithm that was used for the product development, and then the simplified scalable algorithm. And what we can see is that both algorithms, even with the simplified one, allow to characterize the glycemic load at the same level. So we have the same recipe that are characterized as either low glycemic load, medium, or high, which is very good and reassuring. And this is how it looks for consumers, for users. This has been launched in the Philippines and then thus adapted to in Malaysia, adapted to the culinary preferences. And here there are diabetes-friendly meal plans that I have proposed for 7 days and that are compliant with all the rules that have been defined. So my point here is really that whenever there's an app used, it's always important to look back critically what are the nutritional rules that have been used, what are the simplification steps that have been used to develop these algorithms and apps. So finally, to conclude, here for type 2 diabetes or prevention, what we want is really to minimize the postprandial glucose response after a meal. And now we alluded to that. Now with all the devices, it's very easy to collect a lot of data. This is an example of a continuous glucose monitoring device collecting data continuously for 14 days in different groups of volunteers, and then we have all this amount of data. So how can we look back at that? So in this study, what the group was interested was not only to test several interventions, but really what is the role of the eating occasion? What's the role of the time of the eating occasion? What's the role of the composition, of the ratios? And what digital tools now allow is really to go back from this data and then track what are the diets that are working, what are the components that are relevant. And in this study from the group of Blandine Laferrère, what we see is that actually the number of eating occasion or the time at which the food is consumed is not so critical to influence either mean glucose, the mean amplitude of glucose excursion, largest amplitude of glucose excursion, or the glucose variability, but it's really mainly the carbohydrate percentage, which could be expected, but also the fiber to carbohydrate ratio, sugar to carbohydrate ratio, as well as the protein. And this really allows to then go back and better tailor the meals and the dietary recommendation from knowing what's the health impact to optimize the diet and then eventually the product. So I'd like to conclude on how we can use digital tools for not only analysis, but also to develop tools that are helpful for product developers and consumers, because it can really accelerate and simplify product development, as we have seen with the glycemic index tool. It can allow to compile very large database in order to automatize recommendations on meals and menu plans for targeted health goals. And then finally, it's really allowed to gain insight on food and health relationship via machine learning. So with that, I really would like to thank all my colleagues from Nestlé Research who have generated all this data and worked on these different projects. Thank you very much.